So hello everyone, welcome to this video on electrostatics. My name is Soumik and I am a final year undergraduate engineering student. So in today's topic, we'll be covering a topic under electrostatics, that is dipoles. So I believe the viewers of this video are already aware of the Coulomb's law and the basic fundamentals of electrostatics, that is charges, units of charges and all these things. Still, I will go with a little brush up of the concepts. So here we have in electrostatics the fundamental thing are charges. So charges are denoted here by Q, small q or a capital Q. The SI unit of charge, is amperes second, but we take it as coulombs, C, and denote it by C. So from the Coulomb's law, we actually know the force is electrostatic force between two charged particles is given by K into Q1 into Q2 divided by R square, where Q1 and Q2 are the charges, whereas and R is the separation between them. In a diagrammatic form, we can explain this as there is a charge that is Q1 and here is a charge that is Q2, the separation between them being R. So the force is given by this, and the K is actually called the Coulomb's constant. Coulomb's constant K, and K is actually equal to 1 by 4 pi and epsilon 0. This epsilon 0 is called the permittivity of free space or vacuum. Now for the units, we can see the SI unit of force is newtons equals to unit of K into coulombs divided by meter square. Thus the dimension of K is Newton meter square per coulomb square. The value of K is here is 8.99 into 10 to the power 9 Newton meter square per coulomb square, and the value of epsilon 0 is 8.85 into 10 to the power minus 12 coulomb square per Newton meter square. Now there is a very important parameter called the electric field. So electric field is the electrostatic force. Electric field is actually the electrostatic force per unit charge. So electrostatic force per unit charge, and it is denoted by E. E is electrostatic force divided by unit charge for any charge. Electric field is also a vector quantity like the electrostatic force. So the general expression for electric field is basically electric field, I'm considering the magnitude only, is kq by r square. This is the electric field due to this charge q. Later we'll be taking later there are electric fields that are due to other sources, but here we'll be considering electric fields only due to a charge. The unit of electric field is obviously newtons per coulomb. As it is force by charge. Now let us come to our main discussion on electric dipoles. So what are dipoles? Dipoles are basically a pair of electric charges of equal magnitude but of opposite sign. But as we know, there are only two types of charges possible. So obviously it will be a negative pair of negative and a positive charge. Now in the negative and positive charge, they both should be of the same magnitude and separated by a distance. Now let the negative charge is this negative charge of magnitude q, and we have a positive charge of magnitude q again. The separation between them is, let us say the separation as 2a. Now let this dotted line be the line joining the axis of the line joining the two charges. Now in case of dipoles, we define a parameter for the dipole moment. So dipole moment and denoted by p. So dipole moment p is actually the product of the magnitude of one of the charges and the separation between them is a vector quantity. So we have it 2qa. In case of physics, the dipole moment is from the negative charge towards the positive charge. But remember it, in case of chemistry, it is the opposite of this. So in chemistry, it is from the positive charge towards the negative charge. In chemistry, positive to negative charge. This is the difference. In chemistry, the dipole moment is basically in case of polarized molecules, in which there are separations of negative and positive charges to the electrons. So now we'll be considering a position that is on that is a distance r from the center of the dipole towards and along the line axis that is joining the negative and the positive charges. So this is now we'll be considering for the electric fields now, obviously. So this is the negative charge, and here we have the positive charge. There is a line joining these two. This is the midpoint of the field M. This distance is a on the left side, this distance is a on the right side, as we have taken the distance as 2a in the earlier case. So we'll be considering a point on this axis, point P, that is at a distance r from the center of the dipole. Now this kind of configuration for the charges is called an end-on position. So P is an end-on position. So let us try to find the electric field at point P. Now we know for a negative charge, the electric field is towards the charge, and for a positive charge, the electric field is away from it. Here we have considered the coordinate system as xy, the general xy plane coordinate system. So electric field at point P due to plus will be towards the outside, as positive charge is here, so the electric field due to this charge will be away from it. So the electric field due to positive charge is in this direction, and because of the negative charge, the electric field here will be towards it, that is E minus. The length of the arrows that I have drawn are not up to scale, so try to understand. I'm saying about the directions here. For the magnitudes, we will be taking the separate values and the magnitudes. So electric field due to the positive charge at point P will be given as electric charge due to plus charge at point P is given as, it is obviously a vector. So K, positive magnitude of the charges are Q, minus Q and plus Q. So K into plus Q divided by R square. But here the length here would be from here to here. So this is R and this length is A. So hence the length will be R minus A whole square. And in the positive direction, in the rightward direction, so we will take a positive I cap. The electric charge at point P due to the negative charge will be given by K into minus Q divided by R plus A square. The viewers can easily understand why it is R plus A whole square. This length here is R plus, this is R and this length is A. So this will be the total length of the R plus A. Now negative charge. So here we have negative of KQ by R plus A whole square I cap. The negative sign of the charge actually takes care of the direction of the electric field, and here it is seen it is on the negative I, that is towards the left side, as we have taken that conventional coordinate system. So negative charge, the electric field or negative charge is actually on towards the left side, so it is negative. Now for the net charge we can calculate here. E net at P will be given as E plus at P plus E minus at P. This is actually KQ into 1 by R minus A whole square minus 1 by R plus A whole square, and this is I cap. This value on simplification will yield KQ into R plus A into R minus A is R square minus A square, which is whole square. From simple mathematics we are doing this, and this is R plus A whole square minus R minus A whole square. Now we have a formula of, like in mathematics algebra formula, A plus B whole square minus A minus B whole square equal to 4AB. Students can actually verify that by breaking the square and actually evaluating that. So I'll be directly writing that 4 into R into A divided by R square minus A square whole square. This is iota cap. So which is equal to 2K into Q into 2A into R divided by R square minus A square whole square I cap. Now from the expression of dipole moment, we know 2 into 2a into q is the dipole moment. So we have 2k into p I cap, 2k into p I cap. So we have taken the value of the dipole moment here. So there's no need to give a vector sign, as I have already taken the iota component here, into r divided by r square minus a square in whole square. Now actually the distance between the dipoles, this 2a, that is sorry that is this 2a is very small. So and the distance r, that is for the point where we are taking the electric field P, is very large, that is r is very much greater than a. This actually implies that r square minus a square can be approximated to r square only. So the electric field expression comes out to be 2kp into r divided by r to the power 4 into I cap, which is equals to 2kp divided by r cube I. Now so this is the expression for the electric field at an end-on position. Now let us take one example. In that example, we'll be considering one more parameter, like included in that example will be the electric potential. So with the example, let us take a dipole here, negative charge, negative of q. This is a positive charge, positive q. The distance is a distance p. This is the midpoint of this, and again this is our distance r. So electric potential is denoted by V is equal to work done by electric charge divided by charge. Now work done, I'm not going to the derivation of this expression, but this will give rise to an expression of kq by r. This is due to a single charge configuration. This is due to single charge positive charge configuration at a distance r. We are considering the potential here, Vp. This is the Vp here. So this is a different thing. So for the dipoles, we'll be deriving here for the negative charge at point P. In the similar fashion, we'll get V due to plus charge at point P is equal to K Q by R minus A. These distances are A. This is A and this is also A, obviously. So R minus A is the distance. R minus A is the distance from this to this. And electric potential is a scalar quantity. So there is no need to denote it with a vector. Now V due to negative at point P is equal to K minus Q divided by R plus A. So the net V net at P is equal to V plus at P plus V minus at P in a similar fashion, KQ divided by R minus A minus KQ divided by R plus A, which gives rise to KQ 1 by R minus A minus 1 by R plus A. This expression gives rise to KQ divided by R square minus A square R plus A minus R minus A. This is equal to 2kqa divided by r will be strike off, so 2kqa divided by r square minus a square. So 2 now 2qa is a dipole moment, so we'll be having k into p divided by r square minus a square. Again with the same approximation, r is very much larger than a. Like in most of the problems, it will be given r is very much larger than a. So in this case, will be r square minus a square approximated towards r square. So the potential net at point P will be given as Kp divided by r square. This is the value of the potential. Now we'll be taking up a JEE mains question, that is a previous year question, for as an illustration and an example problem. Now two electric dipoles A and B with respective dipole moments dA minus 4qa I cap and dB minus 2qa I cap are placed on the x-axis with a separation r as shown in the figure. Now the conventional coordinate system is used here, that is x and y, and the negative sign here are obviously because of the dipole moments towards the negative of the x-axis. For the A also, the dipole moment is towards this, and for this also dipole moment is towards this. Now we know the potential expression for the dipoles is given by, at a point P, is given by, or rather directly we can write V at point P is given by Kp divided by r square, where r is the distance from the center of the dipole to the point P point. Now here also, as we can see, the distance r is very large than the separation between the dipoles. So we'll be drawing the picture diagram again. Here is the dipole A and here is the dipole B. Here is the dipole B, and let the point be here where we are taking the value. Now this let the separation between the dipoles as r, and let the point P get a distance x from charge B. So from charge A, the distance is obviously r plus x. Now this is what it is given to be found out, the distance from A at which both of them produce the same potential. So from A we have to find. So let this point P be the point where the potential is same due to both the dipoles. Now we know the potential from the center of the dipole to the point P is given by this expression. So V at point P, V due to A at point P is given as K into P divided by R square. Now this R will be the dipole moment due to A is K into the dipole moment due to A is minus 4qa equal to this K minus 4qa divided by this distance R will be R plus X. They are like, this distance is R, so, and this is X, so this total distance from A to P will be r plus x whole square. So now and the potential due to B at P is equal to, using the similar expression, K into the dipole moment here is, dipole moment for this is, for B is minus 2qa, minus 2qa divided by this distance is x square. Now here we are not taking into consideration the vector components, because we are just considering the scalar potential and directions. Directions are inside the dipoles. So as per the question, when condition VA at P is equal to V due to B at P, or K into minus 4qa divided by R plus X whole square is equal to minus 2qa into K divided by X square. So striking the common terms, qa, negative, negative, we get the expression as 2x square equal to r plus x whole square, or 2x square equal to r square plus 2rx plus x square, or x square minus 2rx minus r square equal to 0. So we'll be factorizing and seeing for the solution, or simply we'll be using the formulas. Anything we can use. So for x we'll be solving. X is equal to minus b plus minus root over of b square minus 4ab, b square minus 4ab divided by 2a. So this will coming as 2r plus minus root over of 8 r square divided by 2. So r plus minus uh, root 2 r. This will give rise to r 1 plus minus root 2. So we'll be taking the positive value here, and r into root 2 plus 1. Now this point will be at x distance away from B. So from A it will be, so distance from A, distance rather a distance from A will be equal to r plus the x. The distance is this r plus this x. So x, so r x will get r plus r into root 2 plus 1. 2 plus 1 equal to uh, r plus r root 2 plus r, is give rise to r into 2 plus root 2. This is the value. So we'll conclude here with this question. And there is one more important thing in case of dipoles, that is finding the electric field and potential at a broad side-on position. So what is a broad side-on position? We'll be seeing here. Now for the broad side broad side-on position, this is actually, there will be a negative charge of the dipole here, the positive charge here. So this is a point on the perpendicular bisector. This point is the M. This distance is A. This distance is also A. So it will be a point here. This point P is called the broad side-on position, and and they are at a distance, and it is at a distance R from the center of the dipole. This is the negative charge, and this is a positive charge. This is a field where this is a place where we can explore the previous principles and the principles of trigonometry for finding the electric potential at point P. I will leave this onto the viewers. So the lecture will be coming to an end here. Thank you everyone.